Hello dear viewers, I am Khan Bahadur, Assistant Professor of Statistics, and you are watching a video from my YouTube channel Statistics by Khan. Dear viewers, I hope all of you will be doing great. Dear viewers, this YouTube channel Statistics by Khan has been created for basic statistics with a view to help the beginner students of statistics, the researchers of all fields, and other learners of basic statistics. I have also a Facebook page and group with the same name, Statistics by Khan. You can visit them for steps related to basic statistics. Dear viewers, for better understanding of concepts in my video, I would recommend you to watch the full video. After watching the full video, I assure you, you will understand the concepts very clearly. In today's lecture, we are discussing the most important theorem of inferential statistics, that is central limit theorem. The central limit theorem in fact plays a vital role in inferential statistics. So let's start the lecture. Central limit theorem is in fact a solution of a problem. That is, either if the shape of the distribution is unknown, or if the shape of the distribution is highly skewed, or the shape of the distribution is non-normal. So in that case, the central limit theorem helps in the sampling distribution of the sample mean x bar. So let's discuss what central limit theorem is. What does the central limit theorem state? It states if the sample size is large, then the sampling distribution of the sample mean x bar is approximately normal. There are different possibilities for the sampling distribution of the sample mean x bar. All of them are depending upon the parent population. The parent population is a population from which a sample has been taken. Now let me discuss all the possibilities of the sampling distribution of the sample mean x bar. The first possibility is when the parent population is normal. So this is the first possibility for the sampling distribution of the sample mean x bar. The possibility is that if the parent population is normal, if the population from which the sample has been taken is normal, and the population variance or standard deviation is known. So then in that case, irrespective of sample size, either if the sample size is large or small, but the sampling distribution of the sample mean will be exactly normal. So x bar is distributed normally with mean mu, and variance is equal to sigma square over n. Sigma square is actually the population variance. So remember one thing, if the population is normal, the parent population is normal, and the population standard deviation or variance is given. So then in that case, irrespective of the sample size, the sampling distribution of x bar will be exactly normal. And usually the students get confused in this scenario. Whenever the parent population is normal and the population variance or standard deviation is known. So then in that case, irrespective of the sample size, the sampling distribution of x bar will be exactly normal. So in that case, there is no need of central limit theorem. So this is the only case which is independent of the central limit theorem. For the rest of the cases, we will have to use the central limit theorem. The second case is when the population is normal, but the population variance or standard deviation is unknown. So in this case, though the parent population is normal, but when the population standard deviation or variance is unknown, so then in that case, the sampling distribution of x bar will be not normal for smaller sample size. So in this case, we will be needing the larger sample size. If the sample size is larger, then the sampling distribution of x bar will be approximately normal. So now the second case is that if the parent population is normal, but the population standard deviation or variance is unknown. So then in that case, for larger sample size, not for smaller, for larger sample size, the distribution of x bar will be approximately normal. So one more thing to remember is that for exact normality of the sampling distribution of x bar, we need two conditions. What are those two conditions? The first condition is the population must be normal, and the population variance or standard deviation must also be known. So these are the two conditions. If these conditions are satisfied, so then the sampling distribution of x bar will be exactly normal irrespective of the sample size. But if both or any one of the condition is not satisfied, then we will have to rely on the central limit theorem. The third case is that when the population is non-normal and the population standard deviation or variance is known. Now, in the third case, the population is non-normal and the population variance is known. So in this case, we will have to use the central limit theorem. And the central limit theorem says for larger sample size. So definitely we will assume larger sample size in this case. So if the sample size is larger, then the sampling distribution irrespective of the parent population will be approximately normal. That is, x bar will be distributed normally with mean mu and variance is equal to sigma square over n. If the population variance or standard deviation is known, so then accordingly we will have to use that in the sampling distribution of the sample mean. But if it is unknown, so then we will have to estimate this from the sample observations. The fourth case is when the population is again non-normal and the population standard deviation or variance is also unknown. Now both of the conditions for the exact normality of the sampling distribution of the sample mean x bar are not satisfied. So then in this case again we will have to rely on the central limit theorem. So the central limit theorem says for the larger sample size. So we will assume larger sample size again over here. So in this case the sampling distribution again will be approximately normal. The sampling distribution of the sample mean x bar is approximately normal with mean is equal to the population mean and variance is equal to the sample variance divided by the sample size. Now again, is the population standard deviation or variance is unknown, so we have used its estimate, that is S square. The fifth case is that the shape of the parent population is unknown, whether it is normal or non-normal. We don't know about the shape of the parent population, but the population variance or standard deviation is known. So then for larger sample size, the sampling distribution of the sample mean x bar will be approximately normal with mean mu and variance is equal to sigma square divided by the sample size. Now let me tell you one thing. If this unknown population is normal, what do I mean? If in fact this shape is normal and the population variance is known, so then for any sample size, the distribution will be exactly normal. So then this case will exactly match to the first case. In both of the cases, the populations become normal and the population variance are known. Now the final case is that the population shape is unknown and the population standard deviation or variance is also unknown. So then for larger sample size over here, the sampling distribution of x bar will be approximately normal with mean is equal to mu and variance is equal to s square over n, because the population variance or standard deviation is unknown. So this is the last case when the shape of the parent population is unknown, whether it is normal or non-normal, and the population variance or standard deviation is also unknown. So then in such case, for larger sample size, the sampling distribution of the sample mean x bar will be approximately normal with mean is equal to the population mean and variance is equal to the sample variance divided by the sample size. Now there doesn't exist a case like this, because even if this is normal but the population variance or standard deviation is unknown, so this condition is not satisfied for the exact normality of the sampling distribution of the sample mean. So that is why we are not discussing the case like this, because this condition is already not satisfied. So these are all the possible cases for the sampling distribution of the sample mean. So this is the beauty of the central limit theorem, that irrespective of the parent population, for larger sample size, the sampling distribution of the sample mean x bar will be approximately normal. So we don't see whether the parent population is normal, whether it is non-normal, but if the sample size is larger, so we don't need to worry about the sampling distribution of the sample mean x bar. It will be approximately normal. If not exactly normal, is in this case it is exactly normal, because the combination which is needed for the exact normality of the sampling distribution of the sample mean x bar is fulfilled. So these are all the possible cases for the sampling distribution of the sample mean x bar. So out of 6, 5 are depending upon the central limit theorem. So this really shows the importance of the central limit theorem. Almost 85% of the cases are depending upon the central limit theorem. So this percentage really shows the importance of the central limit theorem. So in final remarks, I would add that the central limit theorem is a solution of the problem when either the population is non-normal or we don't know about the shape of the parent population, or if the population variance or standard deviation is unknown. So in such situations, the sampling distribution of the sample mean will never be exactly normal. But if the sample size is larger, so then the sampling distribution of the sample mean x bar will be approximately normal, and this is due to the central limit theorem. So in simple words, what is central limit theorem? If the sample size is large, then the sampling distribution of the sample mean x bar is approximately normal. So that's all from my side for today's lecture. Hope this will help you in clearing your concept about the central limit theorem. Thanks for watching the video.